Every car chassis explained. Ladder frame chassis. The ladder frame is the oldest car chassis design, and it gets its name from the fact that it looks just like a ladder. It has two long rails connected by shorter crosspieces. This simple design creates a strong base that holds everything from the engine to your seats. Car makers took this design from horse carriages long ago. Today you can still find ladder frames in pickup trucks, big SUVs, and work trucks. The Ford F-150, Chevy Silverado, and Toyota Land Cruiser all use this trusted design. People still use ladder frames as they are strong and simple. When you need to carry heavy loads or drive on rough roads, this chassis works best. It is also easier to fix. If one part gets damaged, mechanics can often replace just that section. But if ladder frames are known for their strength and resistance to rust, why aren't they the standard in all vehicles? Because while ladder frames are incredibly durable and less prone to rust or metal fatigue, they fall short when it comes to crash safety. Ladder frames don't deform as easily, meaning more force can be transferred to passengers. So although they're built to last in tough environments, they trade off some modern safety advantages in the process. Monocoque chassis. As cars got better, makers wanted designs that were lighter but still strong. This led to the monocoque chassis. Unlike the ladder frame where the body sits on a separate frame, the monocoque has the body and chassis in one piece. This smart design spreads forces across the whole car body. It can be seen in sedans, hatchbacks, and crossovers like the Honda Civic, Toyota Camry, or Mazda CX-5. The monocoque's biggest plus is crash safety. In a crash, it soaks up the impact through crush zones. At the same time, it keeps a strong cage around the people inside. This design also weighs less than ladder frames. This saves gas and helps the car handle better. In 1934, Citroën introduced the revolutionary Traction Avant with a unitary body structure. When a Traction Avant collided with a traditionally built car during a demonstration, spectators were shocked to see the conventional car crumple, or while the Citroën remained largely intact. This dramatic display helped demonstrate that producing a monocoque chassis would demand advanced welding and assembly techniques, setting the stage for future automotive manufacturing. Modern factories use strong steel, aluminum, and even carbon fiber in luxury cars. Repairs can cost more than with ladder frames, but the better safety, fuel savings, and driving feel have made the monocoque the top choice for most cars today. Backbone chassis. The backbone chassis is quite different. It has one strong tube running down the middle of the car. Think of it like a spine that supports all your car's main parts. The suspension, engine, and gearbox all attached to this central beam. A Czech car maker called Tatra created this design in the 1920s, but it was British sports car maker Lotus that made it famous. Their Lotus Eland showed how this simple structure could make a well-balanced sports car. Today, backbone chassis show up in special cars that need unique layouts. The backbone design fights twisting forces very well despite being simple. This helps in handling the car precisely. This is very important for sports cars as its central strength also protects well against side crashes. The main structure stays intact while soaking up the hit. A famous anecdote from Lotus testing shows why this design excels. Engineers placed a prototype Elan chassis on blocks at each corner and had a 200-pound man jump on the center. While other chassis would have flexed significantly, the backbone barely moved, demonstrating its exceptional resistance to twisting forces. But backbone chassis have limits that keep them from wider use. The central tunnel takes up interior space. It makes car layout tricky. Also, while side crash protection is good, front and rear crash safety needs extra support. These issues explain why backbone chassis remain rare. They show up mostly in special sports cars rather than everyday vehicles. Tubular space frame chassis. For the best mix of strength and lightweight, few chassis types beat the tubular space frame. This is a network of tubes arranged in triangle patterns. These triangles create a 3D structure that resists forces from all directions. Think of it as a skeleton for your car. Each tube is placed just right to handle specific stresses. Race car engineers created space frames to maximize strength while cutting weight. This is crucial for racing. Famous cars like the Mercedes-Benz 300 SL Gullwing from the 1950s showed what this design could do. Its special doors were needed because of the high sides of the chassis. Today, exotic car makers and race teams still use advanced versions. The brilliance of the space frame is in its triangles. Triangles keep their shape under stress better than squares or rectangles. By building with triangulated tubes, engineers make an incredibly stiff chassis that weighs much less than normal designs. Building space frames takes precise welding and expert design. Each joint and tube must be perfectly placed to handle forces. Mass-producing these structures is hard and costly, but the performance gains make them worth it for special vehicles, where price matters less than capability. Composite monocoque. This is the peak of car structural design. It's expensive, but it uses advanced materials like carbon fiber. These structures offer amazing strength-to-weight ratios that metal simply cannot match. Formula One racing led the way with these designs. They created protective tubs that keep drivers safe in crashes. These weigh far less than metal structures. Today, supercars like the McLaren Senna, Bugatti Chiron, and Ferrari LaFerrari use these aerospace technologies. Manufacturing is totally different from metal chassis production. Carbon fiber cloth is laid precisely in molds. It gets soaked with resin. Then it is heated under pressure. This creates structures stronger than steel, but much lighter. A single carbon fiber monocoque might take hundreds of hours of skilled work. This is why they only appear in the most expensive cars. Now that we live in an era of electric cars, how do you think electric cars have changed chassis design? Electric cars have created a revolution in chassis design. Engineers call them skateboard platforms. Electric cars do not need space for engines, transmissions, and exhaust pipes. So EV designers put battery packs flat along the floor. This creates a very low center of gravity. It helps the car handle better. It also allows for creative use of space. You can have trunks in front where engines used to be. You can have completely flat floors for passengers. The stiff battery case itself adds to structural strength. Some EVs use the battery housing as a supporting part. This means EV chassis can be simpler while being stiffer than gas-powered cars. Space frame architecture. Not to be confused with tubular space frames, the space frame architecture uses extruded aluminum profiles connected by cast nodes to create a lightweight, rigid structure. Audi pioneered this approach in the 1990s with the A8 luxury sedan. When competitors were still using steel, Audi's space frame reduced weight by nearly 40% while increasing rigidity. To demonstrate its strength during the A8's launch event, Audi suspended the entire car from just 4 small points on its chassis. Today, vehicles like the Audi R8, Jaguar I-Pace, and Ferrari FF employ sophisticated versions of this technology. When Jaguar developed the all-aluminum F-Type sports car, crash tests showed the space frame structure absorbed impact forces more effectively than traditional steel designs while weighing significantly less. However, manufacturing costs remain high. At Audi's Neckarsulm factory, specialized welding robots use friction, stir welding to join aluminum components. This is a process that's several times more expensive than conventional steel welding. This explains why aluminum-intensive construction remains primarily in luxury and performance segments. X-frame. The X-frame was General Motors' distinctive approach to chassis design in the late 1950s and early 1960s, featuring a large X-shaped structure rather than traditional perimeter rails. When GM introduced the 1957 Chevrolet with its new X-frame, its low-slung cowboy Cadillac styling was made possible by this innovative chassis. The lack of side rails allowed designers to create the dramatic styling that defined American cars of the era. The 1959 Chevrolet Impala became an instant design classic, partly because the X-frame enabled its impossibly low profile and wide stance. While no modern cars use a pure X-frame, its influence lives on in designs that use X-shaped reinforcements within unibody structures. Some luxury SUVs employ X-shaped bracing to increase torsional rigidity without adding significant weight. The X-frame excelled at weight reduction and interior space maximization. When automotive stylists first saw the production potential of the X-frame, it unleashed a wave of low-profile designs that defined an automotive era. However, side impact protection was compromised by the lack of traditional perimeter rails. As safety consciousness grew in the 1960s, the X-frame was gradually phased out in favor of safer perimeter designs. Ralph Nader's influential book, Unsafe at Any Speed, specifically criticized the X-frame for poor crash protection. Multimaterial chassis. Rather than relying on a single material, cutting-edge designs use multiple materials optimized for specific applications within the same structure. BMW broke new ground with its carbon core technology in the 2015 7 Series, combining carbon fiber, aluminum, and high-strength steel in a single structure. When BMW engineers tested prototype vehicles against competitors, the multi-material approach provided 30% greater rigidity than conventional designs while reducing weight by up to 350 pounds. Today's Cadillac CT6 uses a similar approach with 11 different materials in its chassis, each selected for optimal performance in specific areas. When GM developed this digital craftsmanship approach, they used more than 50,000 computer models to determine the perfect material for each part of the structure. Multi-material construction offers unprecedented optimization. Mazda's Skyactiv body design uses 1,800 megapascals ultra-high-strength steel only in critical areas, surrounded by lower-strength, more ductile materials that absorb energy in crashes, a targeted approach that would be impossible with single-material construction. From simple ladder frames in tough trucks to exotic carbon fiber shells in supercars, chassis design balances strength, weight, and purpose in car engineering. These hidden frameworks determine how your car handles, protects you, and performs. They are truly the unsung heroes beneath the metal skin. What type of chassis is in your car? Does knowing about it give you new respect for your vehicle? Let us know in the comments and subscribe for more looks inside car technology that show the amazing engineering we use every day.